Hello, in this video I'm going to take a first look at progressive waves, also known as travelling waves. So these are the waves where we've got a transfer of energy through space. So here I'm just going to be going through descriptive terms. I'm not really putting any maths into this. I'm just wanting to get together the language and the descriptive terms that we're going to be using to describe waves as we go through subsequent videos. So let's start off then with the difference between mechanical and non-mechanical waves. So this applies to both progressive waves and stationary waves that we'll come to later on. But we're wanting to think about what is actually oscillating. You know, we said in the intro video that a wave is some disturbance in space which is propagating outwards then through space. So we want to think about what the process is that is turning a disturbance into an oscillation and then propagating that oscillation through space. So in the case of a mechanical wave, we're talking about things that we can think of and describe in the language of classical mechanics. You know, classical mechanics is the description of matter in motion. So really we're looking here at waves which are to do with matter. So this might be a wave on a string. You know, we've got a string is made of matter. You just make a disturbance on the string. So you pluck the string. So the string will then oscillate, and that oscillation will propagate because of the tension throughout the string, because all of the matter is attached. We've got a similar thing with water. We've got mechanical connection between the molecules in the water. So you create a disturbance, the water molecules will then oscillate, and that oscillation will propagate in a similar fashion. We've got sound waves would be another one. Okay, this is working off of pressure instead, but we've still got particles. Well, I say pressure in air. If you've got sound in air, then it's pressure is the driving force behind all of this. But, you know, maybe if it's going through a solid, you know, sound can go through solids as well. And then, you know, again, you've got a very mechanical process of the forces operating and existing between particles in a material. Now, this can be contrasted with non-mechanical waves, where there's no medium, no matter medium that the wave is propagating in. I mean, this causes some problems that we're going to park at the moment. But I'm thinking here primarily of electromagnetic waves. I mean, also gravitational waves, but we're not going to be talking about gravitational waves as much as electromagnetic waves. There'll be multiple videos coming up on electromagnetic waves. And of course, that immediately raises the question of, well, what is oscillating? If we've got light traveling through space, you know, we've got light coming from the sun and it's going through the vacuum, or at least near vacuum of space between the sun and the earth. Well, what is oscillating? If we're saying this is a wave, this is immediately causing us a problem that, as I say, we're going to have to park at the moment until we look at electromagnetic waves in more detail. But this caused a problem for scientists for centuries, really. You know, they were coming up with ideas of things like the luminiferous ether, which was going to be, you know, some substance that was going to exist in space that was going to be the thing that was oscillating. Because, well, how were you going to have a wave if it wasn't mechanical? Well, of course, it turns out that this stuff doesn't exist, and we don't have a mechanical wave propagating there in the case of electromagnetic waves, not in the same way as we do with strings, water, sound, and other such matter related waves. So we come back to a lot of that when we get onto electromagnetic waves, but it is one of the first things you're going to want to think about when you're dealing with a particular wave. What is it that's oscillating, and how is that oscillation propagating? This then brings us to another distinction between transverse and longitudinal waves, where we want to think about the difference in the motion of the energy that's being propagated by the wave and the motion of the oscillators that are part of the material, or the part of the medium that the wave is oscillating in. So let's take an example of the wave on a string. It's the first one I've got on the list here. So if you've got some string and we've got a wave that starts traveling down the string. So we've got some kind of pulse which has been put onto the string. We've done a one pluck on the string, and this is now propagating off to the right here. So the energy is moving off from left to right, but the string isn't moving from left to right. Each point on the string is oscillating, in this case, perpendicular to the direction of the energy transfer. So this is the transverse wave. We've got trans here for the perpendicular motion of the oscillator compared to the motion of the wave, the motion of the energy transfer. So this is what we're seeing on a string or even in water. I mean, it gets a bit clouded with water waves, because when we think of water waves, typically we're going to think about going to the beach, where it does look as though we're getting transfer of matter as well as transfer of energy. And this is because we've got a double effect of we've got the wave, but we've also got the tide. So the tide is causing a transfer of matter. The wave is a transfer of energy. So we've got these two effects operating simultaneously. And that kind of clouds the issue, because it looks as though, well, the wave is moving the matter, whereas you can have a water wave if you've got a perfectly flat bit of water, and then you create a disturbance in the water. You drop your pebble in, and you get your rings that are starting to propagate outwards. Well, the water is oscillating up and down, and the wave is propagating outwards. So again, we've got this transverse motion here with a perpendicular angle between the oscillator and the energy transfer. Now, not all waves are like that. We've got longitudinal waves. Of course, the classic one with a longitudinal wave is going to be a sound wave, where you've got then the direction of the oscillation of the particles on the sound wave is in the same direction as the direction of energy transfer. So here they're parallel rather than perpendicular. Now that raises an interesting point, particularly as we've just been looking in a previous series of videos at thermodynamics and ideal gases, that you don't want to end up getting the wrong picture in your mind about how the air that we're breathing is behaving. It's very easy to come off of the back of ideal gases thinking that a gas is a whole load of particles which have got massive separation between them, that are traveling around at these epic velocities, barely touching each other. You can get too caught up in the assumptions of ideal gases to think that a gas is much more disordered than is necessarily the case. I mean, you can have some gases, obviously, that behave like that. But in terms of the air that we're breathing, if we're going to have a sound wave traveling through it, we still need to be talking about some idea of an equilibrium position that particles in the air are oscillating about. So we haven't got this completely crazed motion going on. Okay, we have got the air molecules are moving around. They've got random components to their motion, but it's still possible, as evident with the fact that we can speak to each other and hear, that we can have we can set up what are essentially pressure waves of high pressure and low pressure oscillations of having particles in the air oscillating backwards and forwards longitudinally along the direction of energy transfer. So just make sure you're not getting an unrealistic picture of how air actually behaves. So, because as I say, it is quite easy to take the ideal gas assumptions a little bit too far. We're still getting something that we can successfully model as oscillations about an equilibrium position as sound is traveling through air. So that's a couple of distinctions that you want to make when you're thinking about waves in general, but here particularly we're talking about progressive waves, mechanical, non-mechanical, transverse, longitudinal. So then when we get on to the more technical terminology that we're going to be using to describe waves, I mean, you'll see a lot of this is just straight out of our simple harmonic motion descriptions. So we want to think of some kind of oscillator where we've got an equilibrium position, and that's where the particle is sitting. The particle that is going to be is on the path of the wave. This is the thing which is going to move as the wave goes through it, as the energy transfer goes through this point. So it starts at an equilibrium position, or at least something we can assume to be an equilibrium position. You know, we're going to be making probably some kind of approximation there. Then it's going to be displaced as the energy comes through. It will be displaced. So in a transverse wave, it'll be displaced at 90 degrees to the direction of the wave. So we're going to get a displacement, which is our distance from the equilibrium position, and we're measuring that. Is a vector quantity. We got, you know, positive and negative, whatever way round you want to put it. So we've got a distance from the equilibrium position. The amplitude is the maximum displacement that we're going to get. And this is just our SHM description of motion that we went through in classical mechanics. It moves off to the side, which is going to create a restoring force, which is going to be pulling it back towards the equilibrium. But of course, when it gets to equilibrium, it's moving quickly, so momentum carries it through, and it ends up going off to the other side, and it just keeps on oscillating backwards and forwards. So we're familiar with those. We're going to be familiar with frequency. This is our number of oscillations per unit time. Usually we're looking per second, because then when we've got oscillations per second, then that is our hertz that we're talking about. So that's just, number of oscillations per unit time. Of course, closely related to the period. The frequency is 1 over the period. The period is 1 over the frequency, because if that's the number of oscillations we've got in 1 second, then if you do 1 over that, that's going to give you the time of 1 oscillation. Again, all stuff that we've done in simple harmonic motion. So that's fine. Wavelength, right, this is new compared to simple harmonic motion. So this is going to be the distance traveled by the wave in 1 oscillation. So again, we're having to make sure we've got here a distinction in our mind, particularly when we're talking about things like distances and wave speeds and such like. We've got the difference between the oscillator, how quickly the actual particle is moving on its oscillation, and how far that is moving, compared to the movement of the wave. So how far has the wave moved will be different to how far has the oscillator moved. The speed of the wave will be different to the speed of the oscillator. So here we're talking about for the wavelength, this is the distance that the wave has traveled in 1 oscillation. And the wave speed is then, that is distance over time. So the distance that the wave traveled in 1 oscillation, wavelength, which we denote with the lambda. So you divide that by the period, that is going to be our wave speed, distance over time. So distance in 1 oscillation divided by time of 1 oscillation. That's our wave speed. Remember in our SHM, we had our V max, didn't we? We had our maximum speed that we had of the oscillator as it goes through the equilibrium position, which, if you recall, was our A omega. That was our V max. So we got a different thing here. So don't get your speeds mixed up. Don't get your distance traveled mixed up, all of this. So, we need to be clear about the 2 different types of motion that we've got carrying on in all of this. Right, last 2, we got phase. So again, I would have mentioned this in simple harmonic motion. Okay, we've got a variable oscillation speed. So for the oscillator, it's moving at a variable speed as it goes up and down. But remember, we can consider this in terms of a motion at constant circular motion, a constant angular velocity that we've got on this. So we can think of 1 oscillation of going up, back to equilibrium, down, and then back to equilibrium. So that's 1 oscillation. of completing the full cycle of the oscillation, well, we can describe that in terms of one circle at a constant angular velocity rather than one oscillation at a variable linear speed. So so that's what we're talking about here. We can then divide up this single circle from 0 to 2 pi. So we're just taking that angle of going from 0 to 2 pi, putting it into radians, and say, well, how far round we are in this constant circular motion is our phase. So if we've made it all the way up and then back to equilibrium, we're halfway through the cycle, we're over here, we're at a phase of pi because we're halfway around the circle. That's all we're talking about here with phase. So it allows us then to talk about phase difference. If we're wanting to compare two different oscillators on the same wave, and we say, well, one of them is at this point, one of them is, say, at this point. So, here we're here and going upwards. That's what we'd say if we were here at this point. If we're at this point here, then we're here and going upwards as well. Well, how different are they in their location within the oscillation, relative to each other in terms of their time through one oscillation, their position in this whole cycle? Where are they? Well, we can just give a difference in the angle. We can say, one of them might be here at, say, I don't know, say that was pi by 3. This one might be all the way around here, whatever that might be, I don't know, 5 pi by 3. We say, well, what is the difference between these? The phase difference, you just subtract one from the other and say we've got 4 pi by 3 phase difference between the two of them. So it's just a good way of describing relative position within a cycle of oscillation. So that's phase. And then intensity, right, the last one here. So this is getting on to an idea of flux. You would have heard of flux quite a lot in lots of different contexts probably. But here we're talking about a power transferred per unit per unit area. So power transferred per unit area, obviously the time is coming into the power part of it. So that's our energy per unit time. So power transferred per unit area perpendicular to the direction of the wave. So this is what we're talking about with flux. So when we're getting on to the intensity of a wave, so we're thinking about how much energy is hitting a certain area. So the energy that's going to be encountered, say we had our ripple in a pond, we've created and it's spreading out. We've got some area here, and we're okay, what's the intensity over here? How much energy per unit time, per unit area are we getting over here? So our energy per unit time, that's our power. And then we've got the per unit area, which we put in here. And this is going to depend on a lot of different things. It's going to depend on the speed that the wave is moving at. If the wave is moving quickly, we're going to get a lot of energy turning up. So we're going to get a greater power transfer. So it's going to depend upon our wave speed. So that's one thing that is depending on. It's going to depend upon the size of the oscillation. That's another thing. If you chucked a big rock in the pond rather than a small pebble, well, a rock is going to create much bigger waves. They're going to have greater amplitude. So it's going to depend upon the amplitude as well. It's also going to depend upon our distance from the source. The further away we are, the more the energy would have spread out over the surface of the pond. If you're closer, you're going to get hit by more of an effect than if you're further away. So we've got something to do with the distance as well. You can see it's built in here that we've got the angle as well, compared to is the wave hitting us full on or is it hitting it as an angle? So we've got a lot of things that we're including in this. Now, we won't be going through we won't be looking at all of these things in our calculations. The one that comes up most is actually to do with the amplitude. We'll do a little bit, I suppose, with the distance and the angle, but amplitude is the one that comes up a lot in descriptions in exam questions. And it turns out that the intensity is proportional to the square of the amplitude. Now, this isn't the case for every single wave. So don't think this is just a universal rule for all waves, intensity proportional to amplitude squared. But we're modeling our waves at the moment with simple harmonic motion. And for SHM type oscillations, then this is the case. And we can get a flavour of this. Let's think of when we've got something stretchy. Let's go back to our Hooke's law. If we got a spring or some bit of rubber or something like that which is oscillating, then we know we've got our work done. We got our half kx squared. That's our energy that if we're stretching something out, this is the work that we're doing. So our energy is proportional to the square of the extension. So that's the square of our amplitude, because the extension is our amplitude. When we let it go and it starts oscillating, our amplitude, our maximum displacement, is the extension that we've stretched it through. So we're getting here a relationship between energy, our work done, and the square of the amplitude. And that's why this is coming into this this description that we're going to be using all the time: intensity proportional to amplitude squared. We'll touch on other bits as well. We're going to get quite often 1/r squared reductions in intensity, because we've got this geometric property of energy spreading out over an area. If you've got a sphere, it's being spread out over the area of this sphere. The area is going to be an r squared approach. We're going to maybe look at things in terms of angle as well. So it's quite easy to just take a component of the energy transfer that's perpendicular to the area, or indeed take a component of the area which is perpendicular to the energy transfer. We don't tend to do much with the speed, at least off the top of my head. I can't think of that coming up very often in questions when we're doing the maths of it all. But at least we can see that there is some immediate logic from what we've done with simple harmonic motion in the past as to why the intensity of a wave should be proportional to the square of the amplitude of that wave. So it's not completely opaque to us. So that's quite a long list of terminology that we've got there, but it is familiar to us off of the back of our work in SHM. So that's the descriptive elements that we've got when we're talking about waves. We need to start putting some maths behind this. But before I get on to putting maths behind all of this, I want to talk about how we're actually going to represent these waves diagrammatically and graphically and such like. It's all well and good being able to talk about them, but we want to draw out our waves in certain ways. We're going to draw them as rays, where we're drawing arrows, just saying, well, here's a wave which is traveling. We do this quite a lot. But when we do our ray diagrams and things like that, we draw in arrows for the path that the wave is taking. We get other cases like when we're drawing the ripples on the pond, where we're drawing these what are known as wave fronts, where we're drawing these solid lines. So what's the difference between these? We've also got various graphical descriptions and diagrams that we can draw, where we're actually drawing out these wave profiles, whether this is the variation at a particular location and how that varies and oscillates with time. So we've got time on the x-axis, or it could be for a fixed time that we're looking at the shape of a wave, in which case we've got distance, some distance d on the x-axis. So we need to think about all of these different ways of drawing out diagrammatic and graphical representations of waves, because they can get a little bit confusing if we haven't picked all of those apart. So that's what I'm going to do in the next video. And then we can start thinking about some maths as well to go with all of this.